Okay, so now we've worked a good couple weeks working with equations, solving and evaluating equations. We want to move on to inequalities. The good news is evaluating or working with inequalities is almost exactly the same thing as working with equations, with one small or one large, I guess, distinct difference between the two. Before I move on to what it is to be an inequality, I'm going to review real quick what it is to be an equation. So let's start with a nice simple one. 2x plus 3 equals 9. So we know it's an equation because it has the equal sign. And the equal sign means that the left-hand side has exactly the same value as the right-hand side, and it works in both directions, that the right-hand side also has exactly the same value as the left-hand side. Now, I know that seems just a little bit obvious, but it's a subtle enough difference to think about, that the equal sign means that it works in both directions. So if I were to put this on a number line, what I'm really saying is that if the left-hand side of the equation, the right-hand side of the equation has the value of 9, meaning it's exactly 9 units away from 0 in the positive direction because it's a positive 9, that the left-hand side has to be exactly the same distance away from 0. So whatever 2x plus 3 equals, I have to find that magic x that makes the whole left-hand side equal 9, because they're equal to each other. They're exactly the same size, exactly the same value. Luckily, we learned some tools that help us do that. Just writing it again for clarity, we're going to solve this using the tools that we learned. The job at hand is to get x by itself isolated on one side of the equal sign and all the other values to the other side. Solving is the same thing as using PEMDAS backwards, right? So we work in reverse order, which means I want to move the added 3 before I move the multiplied 2. So using transposition, I'm going to subtract 3 from both sides. If I subtract 3 from the left-hand side, that 3 becomes 0, disappears, and I have the subtracted 3 on the right-hand side. Clean it up a little bit. Now I'm going to transpose the 2. I have a multiplied 2. If I divide the left-hand side by 2, then this 2 becomes 1 or disappears, and I have to divide by 2 still on the right-hand side. And then when I clean it up, I have x equals 6 divided by 2 equals 3. So the special value of x that makes the left-hand side of this equation equal 9 is 3. So that's what it means to solve an equation. It means to find the unknown value that makes the equation true. And remember, we always checked these by plugging them back in. So 2 times 3 plus 3 equals 9. And we're not really sure if that's true. 2 times 3 is 6 plus 3 equals 9. And 6 plus 3 is 9, which equals 9. And since that's a true statement always, it'll always, always, always be true, we know that we have found the perfect value of x that gives us the left-hand side is equal to 9, just like the right-hand side. So that's an equation, and it gives you an exact value on both sides of the equal sign. Inequalities are a little bit different because the values are not exact. When we work with an inequality, they look more like this. 2x plus 3, and I'm going to choose a different number for 9, is less than 9. This case, when I put it on a number line, then I'm looking to solve for the left-hand side has a total value less than 9, meaning I'm looking for what x values, when I plug them in, will give me values less than 9 on the number line. So all of these can be right values for the left-hand side, because 0 is clearly less than 9, 8 is less than 9, 1 is less than 9, negative 10 is less than 9, all these values on the number line are less than 9. I can't pick for this equation, or excuse me, for this inequality, I'll never be able to actually pick x equals 3, because remember, x equals 3 made this, the left-hand side, equal 9, and less than means that the number has to be smaller than 9. So I can't choose 3 ever. But what else am I not allowed to choose? Or more importantly, let's solve it to figure out what I'm allowed to choose. So to solve this, I'm going to use exactly the same steps I used for the equation, right? Except instead of carrying the equation down step by step, I'm going to carry the inequality. So I'm going to subtract 3 from both sides. And I'm going to divide both sides by 2. So this says the x I plug into here to make this true has to be less than 3. So again, I got 3 for an output, but it's not allowed to actually be 3, because if it equaled 3, then the left-hand side of the equation would be exactly 9, and the inequality says it has to be smaller than 9. And so I show that I don't want to use that by putting a circle at 3 on my number line. So this is the solution, is 3. And that means any number that I pick that's smaller than 3, so any x value smaller than 3, is going to be the right, or is going to make the statement true. Let's test one out. Let's put in 2 times 2. Is 2 less than 3? It sure is. 2 is smaller than 3, so let's put a 2 in to evaluate or to check it. 2 times 2 plus 3 less than 9. We don't know if it's less than 9, but we're going to test it and see. Well, 2 times 2 is 4, plus 3 is less than 9. 7 less than 9. That's a true statement. So 7, I could plug x in, 7 is less than 9 is true, so I could plug in 2. I could evaluate this and put 2 into the left-hand side, and that would be a number smaller than 3. Well, let's try over here. Let's look, because I'm saying this solid yellow line that comes from 3 says all of these x values. So notice on an equation, when you get the answer, you just choose one. There it is, 3. That's the equation. That's the solution. 3, you put it on the number line, you write x equals 3, you're done. But with an inequality, when you put it on the number line, we actually want all of these values that are smaller than 3. There are more answers than only 3. And since there are more answers, we show that by just making a really fat line across the number line. Let's check another one. Let's check -3, just for fun. So if I put in, don't have a lot of room to work here. So if I put in 2x plus 3, just going to write the original down, is less than 9, and we want to evaluate this at -3. So I'm going to put -3 in, 2 times -3 plus 3 less than 9. We don't really know because what we're doing is checking. 2 times -3 is -6 plus 3 less than 9. -6 plus 3 is -3 less than 9. Is -3 less than 9? It sure is. -3 is less than 9. -3 would plot over here, and 9 is way over here. So I know that -3 would be a solution to this equation, or to this inequality. So that checks out as well. So all of these values then become the answer. So I would say, easily enough, x is less than 3. Tells me all the x values that I can plug into this inequality to make that true. So just to prove the point, let's check a value that's bigger than 3. Or let's actually check 3. So I'm going to put 2x plus 3 is less than 9. And I want to evaluate that at exactly 3, because remember I said for the equation 3 is a solution, but for the inequality 3 is not. Well, let's see what happens when I put in 3. So 2, I'm going to use substitution algorithm. I don't really know if that's true yet. So 2 times 3 is 6, plus 3 is less than 9. 6 plus 3 is 9, less than 9. Is that true? Is 9 less than 9? 9 is never less than 9. 9 is exactly 9. It can't ever be smaller than 9 because it is 9. So 9 is not less than 9. Now, I'm going to make a little trick here. I'm going to do just a funny little thing. This is called strictly less than. That means you want all the values that make the left-hand side of the equation less than 9. And so the value that you get out is x is less than 3. That means that the x value you plug in have to be always less than 3. Sometimes 3 is part of your solution. Sometimes you're looking for two things at the same time. You're looking for when does the left-hand side actually equal 9? And when does the left-hand side less than 9? And the notation we use in that case would be less than, and I'm going to use a different color, equal to. So the symbol less than means strictly less than. The symbol less than equal means less than, all the numbers that are less than, and the number that's equal to as well, or the left-hand side, all the x values that make the left-hand side less than, and also the value that makes the left-hand side equal to the right-hand side. And two other symbols that work is you could have greater than, again, strictly greater than, all the values that would make the left-hand side bigger than 9, and all the values that make the left-hand side bigger than 9 and also equal to 9 would be greater than or equal to. And you saw this before in pre-algebra and a little bit in elementary math, where you had the little thing where the alligator eats the biggest number because alligators are really hungry, if you remember that. And so that's how you can tell. You can tell that 3 is bigger than x because the alligator would eat 3 because 3 is a bigger meal than x is. So you've seen this before. You've maybe not evaluated it quite to the degree that we're going to, but you've seen it before. So let's go back here to where I changed my original equation here, excuse me, my original inequality. 2x plus 3 less than or equal to 9. And I put that little equal sign in. And so let's trace through and see what that does to the rest of our work. So I'm going to change it up a little bit. So the first time I checked, I should have ended up with x is less than or equal to, right? So that means that this is no longer strictly less than. It's less than or equal to. So I can write strictly up here. Right, strictly less than. Meaning the equal to part doesn't exist for this symbol, and this would be strictly greater than. All right, so that's still true, right? But let's check our solution. So when I check by putting a number that's smaller than 3, when I put 2 in, now I'm going to get less than or equal, less than or equal, less than or equal. All I've done is change the symbol. Is this still true? Well, 7 is less than or equal to 9. It is. It's less than, so that works. So changing the symbol didn't really change this check on the answer. Let's look at this one. For -3, I'm going to make it less than or equal to now. 2 times -3 plus 3 is less than or equal to 9. And then I solve it following exactly the same steps. -3 less than or equal to 9. It is definitely less than, so it's true. Let's do it over here. Less than or equal to. So when I plug in my value, I'm still looking for less than or equal to 9. 6 plus 3, less than or equal to 9. 9 less than or equal to 9. It's no longer not true because 9 equals 9, and that's part of what I want in the less than or equal to symbol. And so now that is a true statement that is a solution. So one of the things that we're doing different when we deal with inequalities is we want to find a whole bunch, infinite number of values that will make the left-hand side unequal to, by either being less than or greater than, the right-hand side. And sometimes we want all the values that make it less than, but we also still want the values that make it equal to. So let's do a couple quick evaluations, which just means check the solutions. Let's say we have 4x minus 9 greater than or equal to 3. So this time we're looking for greater than and equal to. Well, let's see. First thing, all I'm going to do is the same steps. Oh, sorry, we're not solving at this stage. We are wanting to evaluate this at x equals 2. So we're just going to check the solution, right? We're going to put in 2 to see if this is true. So 4 times 2 minus 9 greater than or equal to 3. 4 times 2 is 8 minus 9 greater than or equal to 3. 8 take away 9 is negative 1 greater than or equal to 3. Is negative 1 bigger than 3? It is not. Is negative 1 equal to 3? It is not. So this is not a solution to the inequality I started with. So x is 2 is not a solution. Let's do that again with a different solution or a different value. 4x minus 9 greater than or equal to 3. And this time we want to check when x equals 3. So 4 times 3 minus 9 greater than or equal to 3. 4 times 3 is 12. Take away 9 greater than or equal to 3. 12 minus 9 is 3 greater than or equal to 3. So is 3 greater than 3? It is not. So it's not an inequality solution. Is 3 equal to 3? It is. So that makes this true, or that makes 3 a solution to 4x minus 9 greater than or equal to 3. It is a solution. Let's do one more. See if I can squish it all up in here. 4x minus 9 greater than or equal to 3. And this time we want to check x equals 4. So 4 times 4 minus 9 greater than or equal to 3. We don't know yet. 4 times 4 is 16 minus 9 greater than or equal to 3. 16 take away 9 is 7 greater than or equal to 3. Is 7 greater than 3? It is. So we know it's a solution without even checking the equals part. So let's recap real quick. Evaluating inequalities is really quite a lot like evaluating equations, except instead of getting exactly one answer out of an inequality, you're going to get a whole bunch of answers out of an inequality. They're going to cover a range rather than a specific outcome. And sometimes the value that you would get from the equation is part of your solutions. That would be when you have a less than or equal to or a greater than or equal to. The value that comes out of the equation when you solve the equation is part of your answer set. And sometimes when we're doing strictly less than or strictly greater than, the value that would have come out of solving the equation is not part of your answer set. By the way, I don't think I said this. If it is not part of your answer set, then you put a circle on your number line, because your number line is how you report your solutions at this stage of your game. And if it's not included, then we put an open circle. And if 3 is included, so once I change this to less than or equal to, if 3 is a part of the solution, then you color the circle in, saying 3 is a part of the solution and all the values of x less than 3 are part of the solution.